Hello again. This is part 2 of topic 1 for exam 3. The last video got a little bit lengthy, and I guess I got cut off at about this point. So on that video we had finished up with reviewing how to use the binomial theorem and Pascal's triangle to expand a binomial. And I chose 1 minus u squared because that's the binomial that we're going to encounter, one of the binomials we're going to encounter. The other one's going to be 1 plus u squared and u squared minus 1. But in any event, that was how we expand. And now we'll see 2 final examples. And I'm going to try to keep the video shorter. So they may be in multiple parts, as this one is. Here we're going to see the same example twice. And it's how to integrate, again, odd powers of sines and cosines. But this is going to show us why it's advantageous to use the smallest odd power. So I'm calling this the short way. So if we focus on the smallest odd power, let me start by recopying the given integrals. We have sine to the 7th of 3x times cosine to the 11th of 3x. And obviously the smallest odd power is the sine. So we'll take one factor away from sine to the 7th. We're left with sine to the 6th of 3x. Recopy cosine to the 11th of 3x. And the factor of sine of 3x that we borrowed, we push over with our differential dx. Go so far as to box it off and write the word save. At that point, we want to look back at the cookbook recipe, which tells us change the remaining factors of that smallest odd power to the other. In this case, change these sines to cosines by the Pythagorean identity. But a reasonable question to ask without having that cookbook recipe would be the fact that this feels like, as I mentioned earlier, that we're reversing the u substitution process. Instead of picking our u and making sure the du is satisfied, we're forcing our du to exist, and then we're going to change the remaining factors to be in terms of the u that produces that du. So if our intent is for this sine of 3x dx to make up our du, the logical question we could ask would be, who's the trig function? What is the trig function whose derivative is sine? And that, of course, is cosine. So therefore, if we could change the remaining factors of sines to cosines, we'll be able to start the u substitution process. And we could do that because, for example, we know that sine, as we talked about earlier with sine to the 4th, we know sine squared plus cosine squared is 1. So if my focus is on the sine function, I'll isolate sine squared. That's 1 minus cosine squared. But if I want sine to the 6th, that can be accomplished by taking sine squared and cubing it, because we, of course, are multiplying the exponents. So therefore equivalent to taking 1 minus cosine squared and cubing it. So that's our plan. We'll recopy integral, change sine to the 6th of 3x to cosines. Okay, here's the way to think of it again. 1 minus cosine squared 3x represents 2 factors of sine, but to account for 6 factors, we're going to have to cube it. Then recopy cosine to the 11th, and of 3x, that is, and sine of 3x dx, that's making up our du. Okay, now this is the time that we can start the u substitution process, because we have forced our du to exist in the form of sine of 3x dx, and we've changed everything else to be in terms of the u that would produce it, in particular that u being the cosine of 3x. And then from here it should be somewhat routine. The differential du is calculated. That would be minus sine of 3x. Don't forget times 3. Differential dx as well. Modify, we get minus 1/3 du. is sine of 3x dx. And going back to the integral, we chose our u to be cosine, so here we have 1 minus u squared. Now is a quantity cubed, u to the 11th. And the sine of 3x dx that remains makes up minus 1/3 du. So all of the factors are accounted for. We can make the change of variables. So I'll bring out the minus 1/3 most efficiently, replace change of variables, gives us the integral of 1 minus u squared, but it is a quantity cubed, and then times u to the 11th and the differential du. Now in the last example, we had a binomial that was squared, and we took it off to the side and FOILed it, because once again you can only integrate a sum or difference of terms that are of the form u to the n. So when we have a binomial that's of degree that's raised to a power of 3 or greater, that's when it's advantageous to use the binomial theorem in Pascal's triangle. So I put a little wavy line there to indicate there's a little break in the integration action. We'll create Pascal's triangle to the third row. So 1, 3, 3, 1 is the power of 3. Spread out the coefficients. Signs of the terms are going to alternate because it's a negative between the two terms in the binomial. Always start positive, negative, just alternate all the way down. And then the pattern of the powers. First term of the binomial, in this case 1, raised to the third power, the nth power. Second term of the binomial, u squared, raised to the 0. And then in each subsequent term of the expansion, we decrease the power on the first while we increase the power on the second. So 1 is squared, u squared to the first, 1 to the first, u squared squared, and 1 to the 0, u squared cubed. And what comes out of this is really just the coefficients as well as the powers on u. U squared to the 0 is 1, so we have 1 minus coefficient 3, u squared to the first, u squared, plus 3, u squared squared, u to the 4th, and minus 1, or just simply minus u squared cubed, or u to the 6th. Alright, so that's our expansion. Little wavy line back to the integration. We have minus 1/3 integral. And now this 1 minus u squared that was cubed is now replaced by this expansion. 1 minus 3u squared plus 3u to the 4th minus u to the 6th. Okay, don't forget we had this u to the 11th. That tags along as well. And before we can integrate, once again we have to have a sum or difference of terms of the form u to the n. So this u to the 11th needs to be distributed. So we copy this minus 1/3 integral distributing u to the 11th minus 3u to the 13th plus 3u to the 15th minus u to the 17th, all with respect to u. Now we're ready to integrate. Again, this is the way I like to do it. I think it's most efficient. Just write down whatever that coefficient is. Open up a big set of brackets, parentheses, whatever you prefer. I like the brackets. They stand out more to remind me to make sure I distribute this negative 1/3 when I'm finished integrating. And now integrating term by term. U to the 12th over 12 minus 3 tags along. U to the 13th integrates to u to the 14th over 14. Plus 3 tags along, u to the 15th becomes u to the 16th over 16. And finally, u to the 17th becomes u to the 18th over 18. And that was a negative, I know. I'm going to fix it. And that's the time ladder constant. So I'll finish by distributing the negative 1/3, so minus 1 over 36. U to the 12th. Okay, the 3's cancel, double negative, positive, 1 over 14, u to the 14th. 3's cancel again, negative 1 over 16, e to the 16th, and finally plus 1 over 3 times 18, 54, e to the 18th, plus a constant. And this is obviously a case where it's convenient to just simply write what u was, and that was cosine 3x. But remember, make sure you write and tell me what u is. Okay, so we'll finally finish up this lesson with an example now that shows the long way. So what if you had not realized that 7 was the smallest odd power and you chose to use the cosine as the odd power to focus on? Well, it's just going to be a little bit more lengthy, as we'll see. You get an equivalent answer. It's not going to look the same, but you can trust that it's equivalent. Alright, so I rewrote the original problem, and let's say I didn't know 7 was odd, and I went with the 11 instead. Well, then I'd borrow one factor, so that becomes cosine to the 10th of 3x. The factor of cosine 3x we borrowed with the differential dx, box it off, save it. And the logical question we can ask would be, if our intent is for the cosine to be our du in the formula for the integral of u to the n, what's the u that produces cosine? And that would be sine. So you're basically just asking whose derivative is cosine. So therefore, if you could change the remaining factors of cosines, in this case to sines, then we'll be able to start the u substitution process. And once again, that's the idea. Make sure you get this idea understood. That sine squared plus cosine squared is 1. That's our primary identity. If our focus is on cosine, we'll isolate that. Cosine squared is 1 minus sine squared. You don't have to show this work if you don't need to, but at that point, if you want cosine to the 10th, that would be the same as taking cosine squared and raising it to the 5th power. So again, multiplying the exponents, that would give us 10. So equivalently, 1 minus sine squared to the 5th. So making that change, we'll recopy integral sine to the 7th of 3x. Okay, here's the way I like to think of it. Without having to, write what I wrote off to the side here, you can think of it this way. 1 minus sine squared of 3x accounts for 2 factors of cosine, but to account for 10 factors raised to the 5th. And we copy the cosine 3x dx that we're saving for our du. Okay, so now we're ready for a u substitution, because again, our du is satisfied, and everything else is in terms of the u that produces it, that u in particular being the sine of 3x. Let me just kind of isolate that so you know it was kind of side work. Okay, so now u is sine of 3x du. Cosine 3x, don't forget, times 3, differential dx as well. Modifying 1/3 du is cosine 3x dx. Back to the integral. We have that sine was used, so here's u to the 7th. Here's 1 minus u squared, quantity to the 5th. And then the cosine 3x dx makes up 1/3 du. So making the change of variables, all factors are accounted for. We have 1/3 integral u to the 7th, 1 minus u squared to the 5th, and our differential du. Okay, and now here's a situation like the last example where we have a binomial to a power. But see, this is why you want to focus on the smallest odd power, because now instead of the binomial to the 3rd power, by choosing this larger odd power, it's raised to the fifth, which is just a little bit more work when it comes down to binomial theorem and Pascal's triangle. So again, when we have a degree of 3 or greater, that's when you want to use Pascal's triangle and the binomial theorem. You don't have to rewrite it. If you just look back, that's fine as well, but building it once again. Okay, there's my coefficients. Spread them out. 1, 5, 10, 10, 5, and 1. Alternate signs because it's a difference. Plus, minus, plus, minus, plus, and minus. And the pattern of the powers. First term of the binomial 1, nth power, n is 5. Second term of the binomial u squared, 0 power. And then the pattern again, decrease the first while we increase the second in each of these subsequent terms. So 1 to the 4th, u squared to the first. 1 cubed, u squared squared. 1 squared, u squared cubed. 1 to the first, u squared to the 4th. And finally 1 to the 0, and u squared to the 5th. So now, and skip as many steps as you want in here. So now at this point, okay, all these factors are 1s. We have 1 minus, again, what comes out of this is really just the coefficients and the powers of u. 5 is the coefficient, u squared to the first, u squared, plus 10, u squared squared, u to the 4th, minus 10, u squared cubed, u to the 6th, plus 5, u squared to the 4th, u to the 8th, and then minus 1, or just simply minus u squared to the 5th, is u to the 10th. Okay, a little wavy line, go back to the integration, 1/3 integral u to the 7th, and now that binomial that was to the 5th gets replaced by what we have just found. 1 minus 5u squared plus 10u to the 4th minus 10u to the 6th plus 5u to the 8th minus u to the 10th, all with respect to u. And before we can integrate, this u to the 7th needs to be distributed. And so doing so, we get 1/3 integral u to the 7th minus 5u to the 9th plus 10u to the 11th minus 10u to the 13th plus 5u to the 15th minus u to the 17th, all with respect to u. And now we are ready to integrate. So break down the 1/3, open up a big set of brackets, integrating term by term, u to the 8th over 8 minus 5 tags along, u to the 9th integrates to be u to the 10th over 10, plus 10 tags along, u to the 11th, u to the 12th over 12, to the next term, negative 10, u to the 13th integrates to be u to the 14th over 14, next term, plus 5, u to the 15th integrates to be u to the 16th over 16, and finally minus u to the 17th integrates to be u to the 18th over 18. Close up my brackets, add the constant. And now finally distributing the 1/3, we get 1/24th, u to the 8th. 5 over 10 is 1/2 times the 1/3 minus 1/6, u to the 10th. 10 over 12, 5/6, so plus times 1/3, 5/18, u to the 12th. 10 over 14 is 5/7 times the 1/3 minus 5 over 21, u to the 14th. 5 over 16, nothing to reduce there, so plus 5 over 3 times 16, 48, u to the 16th, and finally minus 1 over 54, u to the 18th, plus our constant. And obviously, again, a case where much more advantageous to just simply write what U was, and in this case, it was sine of 3x. So remember, make sure you write me a little note telling me what U was at the end if you're going to choose to leave it in terms of U, or otherwise back substitute what that U is. Obviously, you see the problems could get lengthy. I don't think they're really difficult. Everything kind of flows rather neatly once you pass the initial strategy. But the next exam is going to be a take-home exam for that reason. And so it was going to be a take-home exam no matter what, even without this little virus that we're experiencing. Okay, so that's it for topic 1. So we'll see you in topic 2.